Good morning, everybody. I want to let you know a quick announcement that one of the homework on this week's Flipped Physics homework, that is one of the questions use universal gravitation. In our syllabus, we will not talk about universal gravitation until later in the semester, but the Flipped kind of incorporated that into part of the pre-lectures. So that the trip to the moon, the third problem. So I will work out the solution of that problem and I'll send that onto Blackboard since we haven't touched how to do the universal gravitation. The method is still conservation of energy, but really just the particular formula we need for potential energy is different. So I will send that out to all of you, okay, in Blackboard later today. Yeah, it's pretty long. That's why I wanted to send out the solution to you. All right, very good. Today we are starting a new topic called center of mass, also conservation of momentum. So the reason to do center of mass is sometimes it is easier to take a point of view using the center of mass frame instead of using the Earth frame. And we'll talk about what that means in the later. So before we talk about momentum, conservation of momentum, I want to introduce the idea of what do we mean by the center of mass. So like center of the mass, it's where you have all these masses in the object, where is the center is located. So you have already done this checkpoint question, right? Here you have a very yummy donut showing here. What would be the center of the mass for this treat? You can see that assuming the donut is the mass is uniformly distributed, the geometric center will be the center of the mass as well, right? Sometimes you have an object that's not uniformly distributed. For example, you may have more dense mass somewhere and some other places less dense. But here, assuming it's very uniformly distributed, then the center is exactly in the hole, right? And then that should be the center of the mass. And A is correct. So it is possible to have your center of the mass to be outside of the material. You can see the picture that I used in our very first opening page is someone doing a high jump. In your Blackboard weekly folders, I have uploaded a video. I hope you will have time to look at it after the class. It's called the Fosbury flop. The Fosbury flop is this high jump invented by this athlete called Fosbury. So instead of jumping it with your head, with your leg and everything going over the bar, he do this backwards. So because he do it backwards, even though his body is over the bar, his center of the mass is actually below the bar. So he doesn't have to lift his body as high. His center of mass, he doesn't have to lift his center of mass as high, because the higher you lift your center of mass, the more difficult it is. So I think it's a really nice way to show a relevance example in real life where the center of mass is coming to place. So the video is there. You can take a look at that if you're interested after class. Okay, so the center of mass is basically, let's find the center. So how do we do that? When something is uniform, it's easy, right? You find the geometric center. When something is not uniform, then you have to average over different objects. So you can see if you have 100 objects in this, you can have a system that has 100 objects, then you have to average over all the 100 of them. So you can sum them up and then divide it by the total mass. So this center of mass is representing the average location of all the masses. You can have a lot of mass in this location. You have a lot of mass in the other location. So what is the average location for all of these masses? So this is what this formula is telling us. When the center of mass is continuous instead of discrete, instead of having one little point and another little point, all the mass are connected, which is pretty much what we see in real life. Then you have to do the integral to integrate all the average position of all the masses. For a system that has many different objects, you can treat each of the individual objects as a as one mass concentrated as their own center of mass. And then you can treat, let's say here you have two objects. Each of them can be treated as one point concentrated here at their own center of the mass. And then your system has two points together. So you kind of got back to the first equation where you have discrete distributions. Now these formulas now look very abstract, but we will practice using them in the examples that follow. Let's start with a simple, the very first definition, the simpler solution, where we have a system composed of a bunch of particles. Now remember when we talk about particles, this is a physics model, a particle model, meaning that you can view this object as a point, simply a point particle model. So for example, like we said, we're looking at the movement of yourself. How far have you moved, right? So we can treat you as simply a point. If we're viewing far away, look at the airplane, how far did the airplane move? Then we can treat the airplane as a point. We're less concerned about, okay, the tip of the airplane versus the tail of the airplane. It doesn't really matter. We're just interested in that object as a point. So for system, you have many of those little points, and you can define the center of the mass of the system as a point with the coordinates given by this. So you have mass 1 with a position of mass 1 plus mass 2 and a position of mass 2 plus, and so on and so on. If you have 100 masses, you add them to 100, divided by the total mass, 1 plus 2 plus 3 plus 4, and so on and so on, right? So these little r's represent the vector of each of these particles from your origin. So the position of each of the particles. So I'm gonna break it down into X and Y components. So if you're curious about the X position of the particle, then you can plug in the X position of each of the particles to get the position of the center of the mass. Again, if you're interested in the Y, you can plug in just the Y. Now, if you have a third coordinates, you do plug in the Z. But if you only have it in 2D, then you only need to worry about X and Y. Okay, so let's practice this with an example, and then you'll have a chance to do a question on your own. So here I'm giving you an example of a system consists of 3 particles. Particle 1 is a 1 kilogram mass centered at the origin. Okay, so the location of this mass would be 0, 0, right? At X equals 0, Y equals 0. Object 2 have another 1 kilograms located at 1 meter. So object 2 is at 1 meter and Y is 0, 1, 0. And just say 1, 0. Object 3 is this 3 kilograms mass is at this particular point. It will take a little bit of time to calculate the coordinates, but the X you can see is really right in the middle. So the X position is 0.5 meters. The Y position is, you need to look at this right triangle. SOHCAHTOA of sine 60 is the Y position over 1 meter, that's the hypotenuse. So you can get 0.866 if you do the calculation. So that's the location of all these 3 masses. Imagine this is, you have a very light rod. How do you, okay, when do you ever have to use this? You have a very light rod, connect a metal ball here and 2 smaller metal ball here. And these are all like say it's cardboard, a very light, right? It's a triangle, like the cardboard. So you're trying to like figure out a point where you can put your fingertips on it and then you can balance this object. Now, if it's the center of the mass, it's going to balance, right? Well, let me show you what I mean by that. So if I have this pen, I want to find the center of the mass. I just kind of feel it to see where I could balance it. So it's somewhere here. I could balance it barely right here. So I found its center mass is where at my fingertips. So imagine you have these 3 three metal balls, and you have a cardboard sort of in the middle, or some plastic in the middle to connect them. And you want to be able to feel where the center of mass is, right? So you can balance it on your fingertips like I'm doing it with my pen. So we can do a quick calculation to see, okay, roughly where is it located? So I'm going to plug in all these numbers. The center of the mass for the x coordinates is mass 1 times x1. Mass 1 is 1 kilo located at x equals 0, right? Mass 2 is another 1 kilo and is located at x equals 1 meter. So we plug in 1 meter. Mass 3 is 3 kilos, but is located as half a meter. So plugging all these different positions divided by all the masses, right? 1 plus 1 plus 3, we have 5 kilograms total. So you can see the center of the mass is actually going to be sort of right here in the middle, which makes sense. That seems to be where is symmetric point of the system. But exactly where are you going to put your y? Now, geometrically, the center might be kind of halfway, right? But you have a 3 kilograms heavier on one side. You might want to move your fingertips a little bit to be closer to where that heavier mass is. So imagine your center of mass will be shifted up. Let's try to calculate to see if it's indeed true. You calculate the y, and 1 is located at y equals 0, and 2 is located at y equals 0, right? 0. And 3 is located at y equals 0.866 that you just calculated using your geometry. And you do the calculation is a little bit above halfway. It's 0.52 meters. So the location of the center of the mass is going to be 0.5 meters and 0.52 meters. If you put your fingertips at that point, you are going to be able to balance it. So this is a quick example of how we use this equation to calculate the center of mass, which is this complicated, looks complicated, but when you break it down, it's really just plug in the mass one by one, right? So we have worked on one example using this equation. Okay, so now let's try to do it ourselves. I have a question here. I give you 4 evenly distributed square floor tiles, and they're laid out in L-shaped. So this is one of the tile, this is another one, 3 and 4, and we want to find the x coordinates of the center of the mass. Now, the equation that I gave you, right, is sum of each individual point particles, mass times their position, divided by the total mass total. This is for point particles. Here, you don't have a point particle. You have 4 square tiles. So what can we do? Can we reduce them to point particles? So let's look at this tile over here. I'm going to treat it as one point, all the mass concentrated in the center of this tile, right? So we're going to treat this as if I have a point right here. Okay. And likewise, for all of them, you can think of this tile is concentrated in the center. So for this tile, is concentrated, is as if you have a mass concentrated in the center, and this one is here, this one is here, okay? So that's just a hint. I give you this hint. So now, instead of an L-shaped tile, you have 4 point particles, each of them at a different location. Can now you find the x coordinates of the center of the mass, okay? All right, so I'm gonna give you a couple minutes to do this in your group breakout rooms, and then when you come back, you could vote. Okay. Okay, 10 more seconds. If you haven't voted, please do so. All right, any last minute vote? All right, I'm gonna go ahead and close this, okay? This is our results, and you can see we have quite a lot of different variations. For the center of the mass, find the x coordinates for this shape. Okay, so as I said previously, we want to reduce this into 4-point particles. Each of the 4 tiles can be viewed as all of its mass concentrated at the center. So so I labeled it 1, 2, 3, 4. Okay. All right. So do we know the x coordinates for 1, 2, 3, and 4? So what is the x coordinates for 1?
0.
Yeah, 0. So I can say this is 0. And what about 2?
0.
And 3?
And 0.
And what about 4?
1.
1 meter, yes. So this is at 1 meter. And all of them have the same mass, right? So I can really just say m for all of them. I don't really have to differentiate it. So mass 4 has a mass m at 1 meter. And you add all the masses together, 4 of them, 4 masses, 4m. Okay, so be careful, this is 1 meter. This is little m representing mass. So m and m cancels. You don't really need to know how much their mass is. You can find they're at 1/4 of a meter, right? So 1/4 of the meter. And if I indicate it on the graph, the center of the mass will be here. I mean, in the x position anyways. The y, we can do the same thing for y. Plug in the position for y. The y position for this, so this guy is at 1, 0. This is at 0, 0. This is at 0 and it's 1 meter above. See, it's 1 meter above. So it's 1. And this is another 1 meter. So 2 meters above the origin, right? So it's 0, 2. And you can plug this into a y coordinates to figure out where the center of mass for the y position. And then eventually you can plot it on the graph. So the correct answer is D, okay? So we simply are utilizing this equation to find the center of mass. Any questions for this one? Any questions? Okay, now let's look at another example, and this is a continuous distribution. So instead of having all the masses scattered around, we have a continuous distribution. So for example, you have a uniform rod with mass m and length L. So I'm asking, where is the center of the mass of this rod? Actually, you don't have to calculate, right? You will tell me. So here, right, look at this picture. This is where the rod is. And I ask you, where is the center of the mass? What would you tell me?
In the middle?
Right in the middle, yes. Because this is a uniformly distributed object. So you find the center is right in the middle. But I'm going to use this simple example to show how would you calculate it for a continuous distribution. And of course, you should get a result that's right in the middle. But this is more general. Even if you have a non-uniform stick, let's say stick where half of it is made of metal, half of it made of plastic. If you have such a situation, then you do need to do the integral to find out. And in that case, we can, or if you have a density that is a function with your position more complicated, you can still find out. But I'm just using this as an example to show how do we use this equation. Okay, so you can see that instead of adding up, right, we were doing this earlier. the summation becomes integration. Instead of adding up each of the masses, we're adding up the integrating all the little masses, right? dm. So if I evaluate this little dm, a small chunk of mass on my rod, and I want to represent it in terms of dx, the position. Okay, so I know that you can think of this as doing a density or doing a proportion. So if I do the entire rod has a total mass m and a total length L. If I'm looking at only a small chunk of mass, which is dm, corresponding to this little small chunk of length, which is dx, right? So how is dm and dx related? It turned out dm is mass over L times dx. You can also view this as sort of a density for the rod, a line density, assuming that this is a very thin rod that only has the length. But you can simply do this using the proportion relationship, like I said here, and you'll get the dm is m over L times dx. Okay, so plug it into your equation that the x position for the center of the mass is divided by the total mass. You adding up all the masses. So little dm, integrating the dm, each of them at a different location x, right? So each of them at a different location, and that's a variable called x in the x direction. So plug in dm, mass over L times dx. So you're really just integrating over x dx. And m is a constant that cancels. Okay, so using our mass knowledge, this integration becomes 1/2 x squared from 0 to L. Plug in your limits and you get your x position is indeed at half of the length in the middle, right? L over 2, just as we expected. So this is just a quick example showing, okay, even if you have a continuous distribution, we can still find the center of the mass. Basically, it's the average of the mass of the position of the masses. Now, what if you have an even more complicated object? Say 2 different masses connected by a string. Maybe an axe and another metal ball or something connected by a string. You give it initial speed, the V naught, from the initial speed at 45-degree angle, assuming there's no air resistance. So the object is doing all kind of crazy things in the air, flipping, flopping in the air and spinning. So is this statement still true? So someone claims during the flight, even though it's flipping and flopping, if you focus on the center of the mass of this object, of the complicated system, and it looks like it's still a parabolic trajectory. Just intuitively, do you think this is true or not? We're gonna get a quick poll on your thoughts. You don't have to think of a reason, just what's your gut reaction? What do you think it is? Okay, all right. Seems like I've gathered majority of the vote. Let's take a look at this together. I'm gonna go ahead and turn it off. So majority of think yes, it is true. If I follow the center of the mass, it's still a parabolic form. Okay, so now let's take a look at a demonstration of this scenario. Okay, so very quick video just to show that indeed the center of the mass of such a complicated object still looks a parabolic trajectory, even though the rest of the object might be flipping or flopping. It turned out that this is sort of like the video that we just see, right? The hammer might be flipping, flopping, but the center of mass is still following trajectory because the Newton's second law still applies to a complex object. Now it's just you have to concentrate it on the center of the mass. Previously, we have done all of the analysis really with the point particle model, right? Everything we treated as a point. Now this object is not a point anymore, but if we follow the center of the mass, it still behaves just like a point particle. So the acceleration of the center of the mass can still be calculated using the net force divided by the total mass. So Newton's second law still applies to the center of the mass. Okay, now if your external force is 0, then the center of the mass should not change its position, or it stays, then the center of mass should not change its acceleration, and should not change its speed. Because if your net force is 0, then the acceleration of the center of the mass will be 0. Okay. So go to this checkpoint question you guys have already done. Let's take a look at this. Now you have a system, now have 2 different objects. So we'll treat these 2 together as one system. 1m and another bigger object as 2m. There are 2 forces on the object, on the system. One of forces pointing to the right with F, 2 F's pointing to the left. Okay. So what can we say about the acceleration of the center of mass of the system, right? If this is your system. Well, this is really just a direct application of Newton's second law, right? Now net force, you have a 2F to the left, 1F to the right. So the total force would be F, right? But it's to the left, right? So 2F minus F, right? Give you 1F to the left. And divided by the total mass, you have 2m, another m, or 3m, right? So the acceleration really be F over 3m to the left. That is A. That is number choice B. Okay. Okay, so you might wonder, well, how is this even more useful? Now let's look at a more relevant example. Here you have 2 people of the same weight. They hold on to a massless pole. So you can treat this as very light, right? No mass you need to consider. You don't have to consider the mass of this pole. They're standing on ice, which indicate that you don't have to think about friction. And the guy on the left starts to pull it, and you can see that they might coming together. So eventually they meet, these 2 people meet. Where would they meet and why? So what do you guys think? Any thoughts on how we might approach and answer this question? And why am I putting this question here? It must be relevant to something we just talked about, right? Any thoughts?
We can start by setting the 0 meters as the origin and then determine the position of the guys from there.
Oh, yes, okay. So let's say this is the origin and the system. Okay, let's call the guy and 2 guys in the rod our system. The system contains with 2 objects, 1 and 2. Each of them had their position. This is at position -3, this is at position 3. So this can give me, what I'm going with this? What can I calculate with this information?
The system center of mass.
Yeah, I can find the center of mass right now. Very good. So I can find the center of mass of these objects with mass 1, position 1, mass 2, position 2, and the total mass. Okay, well, I don't really need to plug in the equation. You can see they're symmetric and they're the same weight. right? Even if you do, you find out that they're located at 0. So yeah, right here in the middle is the center of the mass. There is my center of the mass. Okay, so it's asking where do they meet? I found the center of the mass of the objects right now. And I want to know when someone on the left start to pull it, and these two people are going to meet each other. So how do I answer where do they meet question? I found the position of the center of the mass. So now let me ask you this question. Do you think they'll meet at the center of the mass?
Yeah, they'll meet at the center of the mass.
And why would they meet at the center of the mass?
Because both people are moving towards it.
Yeah, they're both moving towards it. So imagine the system. The system is redistributing its mass, right? After they move, they are all together. What does it look like? When they meet, which means before you have object distributed like this, some mass here, some mass here. And after they meet, they're together. The rod is light, right? So it's viewing as all of its mass is concentrated in the middle. So, which means wherever they meet, it will be the center of the mass afterwards. So here you have a center of the mass before, I'm gonna call it before. And after they meet, obviously where they meet is their center of mass because all the masses are now at that one point. That must be your center. So this is the center of the mass. Sorry, I'm just gonna say, it's two people here. Center of mass after. So it kind of asked the question is where do they meet at the center of the mass? Obviously, when they meet, it must be the center of the mass afterwards, where they are gonna meet, they're gonna concentrate on the center of mass afterwards. But it is also the center of mass before. So the question has become this. This is basically saying where the center of mass after is the center of mass before. So the center of the mass of the system remain at the same location. And is that correct? Center of the mass of the system doesn't change. Doesn't change location.
Professor?
Yeah?
So I'm a little confused. So are we saying as he's pulling it, he's also moving towards, like, it's kind of hard to conceptualize how it's like being asked with the being on ice. Like if you're pulling it, wouldn't you sort of be staying in the same position a little bit and then pulling the other person clear or near to you?
You don't have, since you don't have friction, you're not gonna be able to stay in that place. So even if here is the left guy starts pulling, the right guy doesn't pull, the result is both of them are moving at the same time to the center.
Okay, that makes more sense.
Okay, so, and do we agree that once all the masses are concentrated together, which means they meet, where they meet, that is the location of the center of the mass of the system then, right? So I'm saying, what I'm arguing is the system center of the mass is here and they are moving, right? I'm arguing the center of mass of the system did not move at all during the process. Even though the other parts of the object are moving, the center of mass did not move. How do we know it didn't move?
Because both guys are accelerating at the same rate, and therefore there's no external forces acting on the system?
Yes, yes. If you view this as the system, the acceleration of the system is the net force on the system of the net mass. The guy pulling, those are internal forces, and they're on ice, is frictionless. There is no friction. So you don't have any external forces in the horizontal direction. So the acceleration remains zero. You know that the center of the mass must remain in the same location. right? Regardless of the other parts might go crazy, the center of mass still remain in the same location. So they're gonna meet here at 0 meters. So we can see there are kind of 3 steps into this logic. First step is figure out where the center of mass of the system right now, before it's after it pulls, and know they're going to meet at the center of mass after they pull together, and we argue that center of mass doesn't move. So they're still gonna meet at the 0 meters. Okay, now let's look at trying to look at a variation of the problem on our own. Right, now we have 2 people with different masses, one 2m and one m. Again, they have a massless rod. The big guy pulls himself toward the little guy. Where would they meet now? Okay, just a little variation of the problem as we see. Okay, I'm gonna give you guys a couple minutes to discuss this, and then when you come back, you can go. 10 more seconds. If you haven't voted already, please do so. All right, let's go ahead and close this and we'll take a look at it together. So it seems like you, most of you agree, a majority of you agreed on one answer. Can anybody tell us how do they find the question, answer to this question, where would they meet? So how do you calculate where would they meet?
We find the center of mass.
Yeah, we'll find the center of mass before they start pulling, and they will meet at the center of mass. Obviously, where the location after they meet is the center of mass then, and we argue the center of the mass did not move because again, you don't have external force. Excellent. So let's find the center of the mass together. M1 is 2m, is located at -3 meters. M2 is 1m, is located at 3 meters. Oops, sorry. And a total is 3m, right? So we have -6m plus 3m over 3m, which is going to be -1 meters, right? So the center of mass is at -1. That's where they're going to meet later. So right here. And you can see it is a little bit closer to the bigger guy, which makes sense. The center of mass will be more toward the more massive side. Okay. All right. So the next question before we move on to momentums is talking about the velocity of the center of mass. So we did the acceleration. Now the velocity follows, because if position x is m1 v x1 plus m2 x2 plus so on, velocity is the derivative of position over time, right? So the derivative of dx1 over dt is going to be v1. dx2 over dt is going to be v2. So the position follows exact same format. Is the velocity of the center mass is mass 1 times velocity of object 1 plus m2 times velocity of object 2. And again, sometimes it's easier to do calculation, especially collision problems, using the center of mass frame of reference. If we have time, then we might look at an example of a center of mass frame. But if we don't have time, we won't do it. But it's still good for you to be aware that that is a strategy sometimes people use. Okay, so we have a mass m here moving to the right, collide with another object that's at rest right now. So viewing m and 2m as a system, what is the velocity of the center of the mass? So it's really just a direct application of this equation. I'm gonna let you go ahead and vote because I don't think this requires a discussion. So whenever you're ready, you can take a moment if you need to calculate on your scratch paper. Whenever you're ready, you can put in your vote. Okay, any last 10 more seconds. Let's finish our vote in 10 more seconds. Okay, I'm going to go ahead and end this. Okay, all right. So yes, the 1/3 V as choice C suggested is correct. Very good. It's really just to plug in the numbers. There is no too much of a sort of a complicated process here. There are two masses, right? So your center of mass will just be, the velocity will be mass 1 is m times velocity v. Mass 2 is 2m, but it's at rest, so 0 velocity, and 2 of the masses added together. So you have mv plus divided by 3v, which is v over 3, right? 1/3 of the velocity. Moving to the right, obviously. So you can view this entire system as one center of the mass moving to the right with 1/3 of this velocity v here. Okay, all right, so that's all the discussion we're gonna do for center of the mass. We simply figure out how to calculate the center of mass, and also notes under Newton's second law, the center of mass still follows exactly Newton's second law. And then we're gonna do a new chapter called momentum and conservation of momentum. So conservation of a momentum is the second conservation law followed by conservation of energy. The way that we approach it is very similar. So if you already know how to do energy, and momentum is very similar. So we're gonna use a similar structure to approach it. So this new concept called momentum, right? Again, we have sort of a colloquial word of momentum, sort of saying carry something forward. So kind of indicating the speed in our colloquial language. But in physics, the definition for momentum is simply mass times velocity, okay? And momentum is a vector because velocity is a vector. So momentum is going to be in the same direction as velocity. It also depends on the mass. So bigger an object has, the more massive it is, the more momentum it carries. And also the faster it moves, the more momentum it carries. So it will be very interesting to now, let's look at the unit of momentum. We can figure out the unit by looking at m and v. Mass has unit of kilograms if we're using standard units. Velocity meters per second. I realize this is really Newton times seconds because Newton's is MA, kilograms meter over second squared times S is exactly kilograms meter squared, kilograms meter over, meter over second. And sometimes a unit can tell us the feature of this object, of this quantity. Just like when we did work, right? We got Newton meters, it's joules, right? When we do potential energy of the spring, we got Newton meters, right? It's also joules. So work is applying a force for some distance. It looks like now the momentum has a unit of applying a force over a certain amount of time. So you might be able to already guess what your conservation of momentum equation has to be. Right, so just let's put a mental note on that and we will get back to it. So a momentum, if you have, it's a vector. So if you have a system of many objects, the momentum of the entire system is simply the vector addition of all the objects in it. You add up all the momentums, 1, 2, 3, as if there are vectors, right? V1, M2, V2, M3, V3. It's like how we calculate the force, the net force, right? On the object is F1 plus F2 plus F3, adding them like vectors, right? Vector addition. Not like energies. Energies are scalar, so you really just do kinetic energy plus if you have potential, you add all them together and so on, so on. Add them like numbers, but these are vectors, so you have to think about the magnitude, and therefore there's a little vector sign on top of it. Okay, so let's do this. We can figure out what the momentum of the system is. So now consider two cards. We have two different masses. One is M, one is 2M, which was originally at rest. There are two scenarios. Scenario one, this mass is moving to the right. Mass two is at rest. Scenario two, that they're both moving toward each other with the same velocity v. So if we compare the magnitude of the momentum of the system, which one is larger? Okay. So go ahead and I will give you a couple minutes to discuss this in your breakout rooms. And you can take a screenshot before you. Okay. All right. So 10 more seconds. Let's wrap up our vote. All right. Any last minute vote? Okay. And then I'm going to go ahead and close the poll. So this is pretty much, this is our results. Were quite spread over these 3 different choices. We were going to calculate, compare the magnitude of the momentum of the system, right? As you realize, to do vector addition, here all the vectors are in one direction, either to the left or to the right. So we might want to define a positive direction, right? So you could label it as positive x hat or negative x hat as indicating its directions. So I'm just going to say to the right is positive. You could say to the left is positive, and that doesn't change the results. So in scenario 1, the system has 2 objects, okay? Object 1 and 2. Object 1 is mass 1 times velocity v, and it's pointing to the right, right? So it's in the x hat direction. So you can put a little direction to indicate. And 2 is at rest, which has 0 velocity. So it's just going to be m1, which means it is to the right. Okay, so scenario 2 has 2 objects, m moving with velocity x in the positive direction. The 2m is moving with velocity v in the negative direction. So you can see it becomes negative mv x hat, which is mv in the negative x hat direction, right? So it is pointing to the left. So you can see if we were to compare the magnitude of these, they're both mv, but one is pointing to the right and one is pointing to the left, okay? So the answer is that they have the same magnitude. C is correct. Simply they have different directions. In our calculation, when we do conservation of momentums, once you define a positive direction, you could remove the vector signs. You could simply say P is equal to mv minus 2mv. For this case, for example, it would be negative 2m and negative mv. So once we, when we do problems later on, define a positive direction, and then you can remove your little hat and use the, let the sign to decide, to show in which direction it is. Just like when we do F net equals ma, right? We define a positive direction, right? And we'll say mg minus normal force equals 0. So we have already removed our vector signs. And we use our signs, positive and negative signs, to show that we already think about the direction of the force. Okay, just a little heads up what's coming up next when we do these kind of calculations. So we can use momentum to rewrite Newton's second law. Recall Newton's second law is F equals ma, but F and momentum are also related simply because you can rewrite acceleration as in dv over dt, the derivative of velocity versus time. That is how acceleration is defined, right? So because we know acceleration is dv over dt, we can do this substitution. And mass doesn't change. When mass is constant, as most of our problems are, you can sort of move mass into your derivative sign. So your derivative of mass times velocity over dt. Mass times velocity is what? Is momentum. So F net is d momentum over dt. That is Newton's second law. So Newton's second law have this format. Also, you can have it in this format. They represent the same thing. The extension to Newton's first law is when there is no external force on the system, which means F net is 0, then there is no change in its momentum. So if momentum doesn't change as time goes, which means momentum is a constant, it does not change when time goes, right? So the difference between internal and external forces is that only the external forces can change the momentum of the system, just like how in energy transfer, only external forces could change the energy of the system. So external forces do work, transfer energy through work, right? Also, it transfer momentum. And as we will talk about later, we will transfer momentum through a quantity called impulse, okay? So a lot of our problems, most of our problems consider there's no momentum transfer. So if we have two objects A and B that they interact with each other, but there's no forces acting on the system as an external force. So the momentum will remain constant, which means P over dt will be 0, P will be constant, which means P initial and P final should be the same because there's no momentum change, okay? All right, so there's one last question we are going to answer. Is you have a system of two cards where they're connected by a spring. At first, the spring is compressed and you let go. You can see the spring push them and they're being pushed to the two sides, right? They're being pushed to the side. And the spring is very light and you don't have to think about the mass of the spring. So the question is, what is the total momentum of the system after it's being released here? Okay, think about how what we talked about previously can apply here. I'm gonna let you take a screenshot and then we will have a couple minutes to discuss in our breakout rooms. All right, so 10 more seconds. Let's wrap up our vote in 10 more seconds. Okay, any last minute vote? All right. Okay, so I'm gonna go ahead and end this. This is our results. Looking at choice A and C seem to get more of the answers than the others. A says is 0. C says is MV to the right. Noticing that we don't really know what V is, right? Okay, so take a look at the question. What we were discussing earlier is we're saying if there's no external forces on a system, then the momentum of that system will remain constant. So if you view the two cards and the spring as one entire system, is there any external forces on the system?
The spring force?
So I'm including spring into my system.
And there's no force.
Yes, the spring force will be internally, right? If you view them together, yes, it's like the spring is pushing this little part of the spring system to the left and part of the system to the right. So eventually, overall, it doesn't affect the system. It's internal force, right? So if you view them, the entire whole thing as a system, the external force is 0. Or gravity, normal force, they're all balanced. So there's no external force overall. So the momentum P will remain a constant. So momentum initial equals momentum final. Momentum initial is the 4. They're at rest. So momentum initial is 0, equal to momentum final. So whatever momentum they move at the end must be equal to 0. And you might wonder, how is that gonna be possible? They're both moving, but they're moving in opposite directions. So if one is m, one is 2m, they have to move in such a way so that their momentum is still 0, which means m v1 and minus 2m v2, they're opposite signs. They have to add up their momentum together to be 0. So it's a constant, just like what they had. And that's, in fact, a lot of times we do conservation of momentum. This is how we try to figure out how do we do the problems. We will see more of those problems later. But here, the momentum of the system is 0, simply because there is no external force on it. So to a little heads up, what's coming up next is we will discussion conservation of momentum. And again, you do not have to memorize the equation. It will be very similar to conservation of energy. It will be momentum final minus momentum initial. If you have a change in momentum, you have a momentum ins and outs. The reason I didn't say momentum in minus momentum out is because momentum is a vector itself. When you say in and out, it's really simply just saying the transfer in the same direction as you had before or in the opposite direction. So I'm gonna say in and out, I group it together as the entire momentum transfer, right? Because the direction will take care of the signs. Unlike the energy, if you have energy output, you have to minus that. But a lot of our systems is with no energy, with no momentum transfer. So for pretty much all the problems we consider, we can all reduce it to a momentum final equals momentum initial, as momentum remain a constant during a equation or a process. Okay, so that's all for today. For next week, we'll continue to work on more energy conservation momentum problems, and have a good rest of the week. Okay, see you guys next week.
Thank you,
Thank
Professor.
you, Professor. Have a good rest of the week.
Thank you, Professor.
Have a good weekend.
Thank you, Professor. Have a good weekend.
Thank you, you too.